Okay, I want to do a quick video to kind of summarize this YouTube video I found regarding, let's see if this focuses correctly. Yeah, there's a title down there, Old Transformer AC TIG. And what this design's showing is, it states a TRIAC, but it's actually a TRIAC. So it's basically an AC diode. And what's going on here is I really thought the design was really neat, where a rotary switch is used to switch between this series of Zener diodes. So basically it would affect the gate on this TRIAC, or you could have a silicone controlled rectifier, I guess. I gotta think about this. It might not, I'm trying to know exactly if one or the other for the DC electronegative, or the negative cycle of the alternating current waveform. So you can see here where he's demonstrating basically as you change your setting for your gate on your TRIAC, or it seems like it'd be an SCR also might be able to, but this is where I'm not so keen on the electronics. I need to see the waveforms. You can see where the waveforms cut off more, so that positive cycle stays complete, no issues, and only the bottom part of the cycle is trimmed. Now this is just super simple. I've been wondering over the years if there's an easier way to make the AC balance option, where you basically get the cleaning cycle and then you get the weld cycle for if you want to weld aluminum. And this is basically just your 220 VRMS and 50 Hertz input. You can see the one side, this isn't rectified, goes through the transformer. So this will be your electrode side, ground side, and, or I suppose could be, not vice versa. This would be your negative side. Yep. So, and then this negative side's controlled via this, again, TRIAC, even though it says DIAC, and switching the gate of that TRIAC via these Zener diodes. Now this goes back to this modified tombstone article, where now the Gregory Hillstrom site's not up, but the Internet Archive does have, where was that? Right here. And he does a good job of detailing the schematic. We have focus fun. The schematic here, where you have the waveforms along with the schematic. So you can see how that SCR in this instance is chopping both sides with this design. And we look at the schematic, and maybe that's why the TRIAC is used. And I have to think about this a little more, because I'm not critically thinking about this. I just want to document this basically as a thought exercise to show some example schematics and how these designs were performed by these gentlemen to create what they wanted to suit their needs. Now this design using the SCR, you can see the inputs coming in. This is 336 volts, so let's say 240 volts, input 60 Hertz. The one side's using the dual SCR, and you can see here, similar, there's a gate control, but they're using a DIAC on these gate control with potentiometer, because this is going to be for the foot, or the dial control, to adjust that gate on these SCRs. So maybe the dual is used to, and I have no idea. I'm not an expert at this, so I'm totally a novice. I'm not really even a great amateur. I don't really understand why both of these use that for the positive cycle and the negative. I don't know. But then you can see that this circuit design goes into the transformer, and then later he has a design here where he's DC rectifying. I think he shows that up higher here. Yeah, with the rectifiers. The schematic. Yeah, there's a schematic here. Yeah, right here. So this is where he's rectifying, and he's got a microwave oven choke. I've seen comments where some suggest do that on the negative side, not the positive side, add a choke. And then others, this is more a constant current application. If you want a constant voltage, you'd put capacitors with bleed resistors on them. And speaking of, this all came about because when I was watching this video, there's a comment down below. Somebody was trying to research the Syncrowave. And, where was he at? He's further down. Yeah, wondering about the Syncrowave design. So, I had remembered and mentioned there's these IGBT waves, where basically you have your DC AC coming in, and you're controlling, well, excuse me, the DC coming in, and you're going to control switching between DC electronegative and DC electropositive, and then coming out here doing some other, whatever it is you're going to do to that waveform. I don't know if it's like an isolation transformer is going on, but you basically, with a controller to control the basically gates on these IGBTs and the H-bridge, you're controlling that duty cycle of what would be ideally, instead of you saw other chopped up form, you would have with these newer designs, IGBT designs, you wouldn't have this lag time of, let's see, where's that, 20, yeah, here we go, somewhere in this, there's, there we go. You wouldn't have this lag time at the 0, and then, your less duty cycle of the pure sine wave here, at least 60 hertz. Now, you're limited to 60 hertz, excuse me, or 50 hertz, whatever your mains is. Now, you might be able to double that if you had two waveforms offset, two different phases, but we're not going there. So, in contrast, like I was saying, 0 lag time, and this would be the more modern IGBT design. Though, I was wondering when I was looking at schematics, I was like, well, what are the schematics for those Syncrowaves? And I'm looking, I'm like, oh, they have an SCR on the Syncrowaves. So they're like using 4 TRIACs or 2 dual SCRs. And then, you got controls on those going back to the controller, but then you're outputting to your, eventually, I think it's over here, yeah, over here, your your electrode and your work eventually. So, yeah, and then the modern design, and this is super quick overview, I did not detail that in detail, well enough. It's just kind of to remember to look back at some of these schematics I found. And with the newer Syncrowave 210 design, you see here the IGBTs are used for those. This is an actual H-bridge. It's the more modern design, not the older SCR design, which I don't know. Maybe there's benefits of the silicon IGBTs that can handle higher current weren't out yet, or having enough, you put them in parallel to handle that current. So this seems like a simpler design, but basically, my understanding is you're going to get the better waveform with that inverter design. So basically, you're taking DC and creating pulse DC, positive and negative, to create an AC-like square wave that, you could, like an inverter would be a modified square wave inverter design, but then you pulse the wave, and you basically have all these little micro pulses to make it look more like a sine wave, and then you just use capacitor and inductor, capacitor to smooth out, say a smoother sine wave, pure sine wave, and then for the current pure sine wave, you'd have that inductor calculated to be whatever that's needed to be for that range of operation. So I think I explained that correctly. I also took a look to verify that this design's schematic is showing that part there is actually this here. It's not a DIAC as noted. On the schematic, it's actually a TRIAC, because a DIAC is, doesn't have a gate. So I thought it looked a little different. And then here you can see Wikipedia did a good job with detailing the waveforms. This is where you have a TRIAC. You can see the schematic and how that waveform you can see here is triggered to latch or not latch, I think is the correct terms. So basically turn it on or off. And then the thyristor, you can see here, the effect on the trigger voltage on that gate to control when that waveform is coming through, basically is on or is not on. So I think I went through what I wanted to. There is one more homebrew do-it-yourself welder. I mean, this gentleman, I didn't pull up the video, used microwave oven transformers and literally totally completely from scratch built his welder. And there's a similar design for using these SCRs on either a TRIAC or a DIAC to handle chopping up basically that waveform, and then being able to, you know, with that fine-tune your controls. Super neat, I think, studying this. It sounds super ghetto the way I'm explaining. Hopefully it's not too bad. Though this was just, I had to document it because I was just like, oh, cool. I've wondered an easier way to only chop half the waveform. And I've not seen where the one side is impacted. You can see the other side's a little bit impacted, but really insignificantly compared to the negative side. You know, so basically positive side 0 and the negative side. If some don't really understand electronics, and I'm not the best at explaining, but I'm trying to kind of get this, like I said, documented for myself, and then everybody sees this. Hopefully it doesn't confuse them more. It gives them some insight into how these systems work that are like the Syncrowave design, 210, Syncrowave older design 250, with these H-bridge basically to control that. You'd think this is, maybe it is coming off a full bridge rectifier, so maybe that is DC rectified then before it comes in, so you have that yeah, you have a DC waveform, or really just straight line, probably smoothed out with capacitor and inductor, so it's basically just a straight positive DC, and then you just change that to be inverted basically, so you have negative DC, and you switch back and forth to get that alternating current look. And depending on how you smooth that out, is going to be, do you have a square wave, do you have a sine wave, maybe you have a sawtooth wave, and that's how you're going to create that. Then based on that gate control, the H-bridge, the duty cycle being more positive or being more negative, or balance, balance more positive or balance more negative. So you basically can have those balance controls. Now this is a CST 250, so I'm coming back to this, and this is, again, this design, to me, I don't comprehend why splitting off from the AC source, which I'm guessing is actually a real alternating current source. I don't think it's DC rectified before, comes out in two different coils. So you have the one and then the other, and then they're like in parallel, put back together, basically parallel wired back to be positive and then the negative. So if, say, I wanted to modify this, to control, what would be an easier way to take, and take this waveform probably from the positive and negative out further here, so don't mess with any of this circuitry, and then create that duty cycle controlled or balance control circuit. Maybe though that would be something that you could do earlier on right here on this side of the coil. I don't know how it mess with all these different feedback loops, so that'd be kind of funky with that feedback control. Then you get way more complicated. So seems like probably not. So this type of design, you just deal with the output DC, and then other than feedback maybe coming in based on the load out here, maybe having issues. But if not, then you should be able to just, I think, hook up your H-bridge design outside of here, and then you basically just take that DC, convert it back into AC, and then adjust that duty cycle. So, okay, I think that's it. I'm at like 16 minutes. This is like my CST 250 plus other welder design kind of thoughts. I guess I'm kind of refreshing the old Tombstone mod design thoughts, and then kind of incorporating into this newer CST 250 to see, hey, what could I do, you know, like I was saying before. Super simple to get wired to the mains, but it's neat to describe all that as I'm going through, working it out. Where the gaps were, where I could see that's ground, system ground, not equipment ground, I need equipment ground. And then with this also, I really should look at the boards a little more and see if somewhere there's a connection so that these here, this here, when it senses a load, knows to, maybe there's a plug somewhere, a spade connector where I can hook up the solenoid to trigger that solenoid for the gas flow, and then put a circuit in between there that would be pre-flow. I don't know exactly how I do that so easily. I just don't. But post-flow seems like it'd be super simple, just like a delay circuit, so there's still power going to that solenoid for whatever that delay post-flow time you want to be. Super simple there, but to get this to be like an inverter, add-on inverter for welding aluminum, it just seems like a really fun, cool project, because it does align with these older, you know, thoughts I had documenting for the welders I wound up investing in on, you know, the Hackaday article. So, okay, I hope that helped out anybody, gave them some sources at least for some circuits, proven circuits that do work. Not the best designs, but hey, you know, just think about what, you know, those were, you know, working with, that you're just dealing with AC with no duty cycle, you know, no balance control at all. And, you know, you create suitable wells. People do suitable wells with DC also. It's just, you know, it's option with ARC, TIG, and MIG. So these newer designs probably do improve, but they're nothing like, you know, the buttery smooth controls on the more expensive welders. However, if you don't have the funds, or it's just, you know, maybe you do, but it's just fun to learn how these operate, and you can do that safely, you really, you know, especially if just thought exercises all on paper before, you know, plenty of critical thinking with reviewers before you do anything, you know, live. If you eventually get to that, you know, it's funny seeing some of the comments, people wanting to, you know, 40 years ago rectify their buzz boxes, and that's just converting to DC, which is super simple. You know, they never got around to it. Now these more, you know, controls to fine tune, you know, your output, and then which really I thought was super cool to do the balance control, that duty cycle control, on only one side. Man, that's really neat, worth documenting. So I want to document, you know, check out Zuzuni Agrokubanos, it must be Greek, website, and I never learned Greek, but my grandpa was from there. So anyways, So, but I did look. So, and the gal, some people I've spoken with, that's the gal, that gentleman, yeah, you know, mentioned, hey, you probably don't want to. At least a gal did with, she was like with her children. She's like, yeah, you can have your, you know, you definitely you're entitled to your Greek citizenship, but you'll have to serve in the military. You know, I mentioned I probably wouldn't be able to serve in the military, maybe intel or foreign service. And say, well, still, you'll have to do that for so long. And so I don't know. But anyways, kind of off on a tangent, but super neat, got me excited, so I figured I'd document. And then that got me looking at these schematics to see, hey, like I was thinking, is that right? You know, are those H-bridge designs? And yeah, the Syncrowave, like the gentleman asked from that video, yeah, the 210 definitely is an IGBT design, and I was really surprised to see, which kind of got me back to looking at the other SCR, thyristor, TRIAC, DIAC circuits. Oh, this is a H-bridge using TRIACs, or maybe those are two dual SCRs. So it looks like it's SR1. So you know, I don't know, or maybe they're individual SCRs. And then that term using, you know, thyristor SCR, maybe TRIAC, they're used interchangeably. I don't know. I have to study that a little more detail. But yeah, neat stuff. So 21 minutes, I'm going to get going. Be safe, stay healthy, and until next time, bye for now. Learn something new, rescue, restore, repurpose. If you have to repurpose, try to save maybe as you can original, or, you know, modify, upgrade those higher quality made in the USA products with, you know, what you can do, either afford or, you know, with the resources you have available. Maybe you want to try to come up with a neat, novel way. You know, it's cost effective, or maybe it costs more, but you have the parts to keep that item that's designed to last longer in service, and keep it off that scrap pile, the dump pile, you know, the waste bin, you know, keep it in service. Okay, take care. Bye for now.